who is Dr. Kanchan Khemchandani. She is from Department of Physics, uh, Federal University of Sao Paulo, Brazil. So Dr. Kanchan Khemchandani did her graduation from VS College, Mumbai, and post-graduation from UDP, University of Mumbai. She obtained her PhD degree working in a BRC University of Mumbai collaborative project. She then did several postdocs at University of Valencia, Spain, University of Coimbra, Portugal, Research Center of Nuclear Physics, Osaka, Japan, and University of Sao Paulo, Brazil. At present, as I said, she is assistant professor at the Department of Physics, Federal University of Sao Paulo, Brazil. Her area of research is hadron physics, and she has around 60 publications to her credit. She also actively collaborates with theory groups at the University of Osaka, Nara Women's University, Beihang University, Pukyong National University, University of Sao Paulo, University of Valencia, and University of Murcia. So today her talk is on a very interesting topic and very interesting title, with a very interesting title, The Strange and Charming Enigmas of Present-Day Hadron Physics. So, madam, you can begin your talk, and I am sure it will be going to be a wonderful talk, which will be enjoyed by everyone, especially the students. So the stage is yours.
Let me share my screen. Fine. So first of all, it's a pleasure to be virtually be present at the Department of Physics of Bombay University, where I studied, got educated, motivated, and I work in this field today thanks to my education I received during my MSc years at the Bombay University. It's also a pleasure that this occasion is the golden year of the Department of Physics Bombay University. I would hardly like to say that the name is nice, GYAN, but I am definitely far from speaking any of the words which could be called as GYAN. I am going to just talk simple, plain hadron physics research stuff that I do. And I have to, before I begin, I have to say, I would like to say a few words. I am very thankful to all my teachers at the Department of Physics. They were all very supportive and very kind. And we had lots of fun learning those days. And I have visited Department of Physics on several occasions after I got graduated. And it has always been such a pleasure. It's like going back to home. I was particularly impressed or motivated by the particle physics lecture by Professor Anuradha Mishra. They were really enlightening and motivating, starting from the learning relativistic kinematics, where we solved like hundreds of problems. And then we learned symmetries, the toy theory of Feynman. We went over to calculating Drellian cross-sections in the lecture room. I was just reminding her how very often she was always such a strong lady. She would be talking and teaching for hours, and she never looked tired. And she never does look tired. Even today, I have met her on several occasions. We had a lot on our course, and sometimes our regular lectures were not enough. And then she asked us to come sometimes on weekends. So she came Saturdays to teach. And sometimes we had just particle physics lectures, and it went on for like 4 or 5 hours in a row, really. And that was so impressive and so motivating. And I thank you, madam, for those wonderful lectures. And I have also participated in this LightCon conference in 2017, which was nice because then I got also to see how many young people are in the nuclear hadron physics research field, more particle physics. That was also very pleasant. And whenever I have needed you have always been so kind and supportive, and that is something I have to thank you for. Also here in the audience is the most popular Professor Rangwala. I am so thankful to him for his lectures too, and for being so kind. I have met him also on all occasions I visited Bombay University at least. And he always is as charming, as funny, and as young he always looked. I already told him, but this goes on record. He doesn't want to share his secret with us, but just to keep the records. Okay, now I'm going to go over to talking on hadron physics, but just quickly before I talk on hadron physics, let me talk slightly about my journey, which took me from Mumbai to Brazil. Although already all this has been spoken, but just a little bit I would like to say. I did my bachelor's from Vivekanand College in Chembur, and I did MSc from Bombay University. After that, I wanted to do PhD. I remember actually those days I even told Anuradha madam that I wanted to do PhD with her. We had a few discussions, and at that time I had no fellowship yet. And then appeared this opportunity, which was a BRC Mumbai collaboration. And there was going to be an interview. And Anuradha madam encouraged me, and she said, you should go to this interview, because if you have a fellowship, it's always good and you will certainly learn. And she wasn't wrong. I had lots of fun in BRC, and it was good to have a fellowship. And after my PhD, I had an opportunity to go to University of Valencia. I just want to say a bit of how I got this opportunity, because this is important for young people to know. Is sometimes we do not know what we have at our hand. I got this opportunity because there was an international conference being held in Puri. When I think I was still writing my thesis, or I had just written it down. And there was this conference. I gave a talk there, and after my talk, which was, I have done my PhD on few body physics. I have a few slides here to tell you a bit on how I have continued with the few body physics. After my talk, at least two groups, one from a university in Germany, Professor Ulrich Mosel and Professor Eulogio Set from Spain, both showed interest and in my work, and they asked me if I would like to go and do postdoc in their groups. Now, both were wonderful opportunity. What I want to tell you here is that I did not realize how important were those days, the conferences, international conferences, or these kind of events which are being organized by our professors and senior scientists around. At least in those days, I think it might still be the same. It's all around the world. A PhD student usually does not have a lot of money to travel around. And networking is important. We are also geographically far from Europe and US. So bringing the international scientists and physicists to talk in India and holding such conferences, it was an excellent opportunity. It is always. So if you get an opportunity, please do not miss it. So I just gave my talk, and then I had these two offers. I remember that in one case in Germany, I had to still apply for a project. And however, in Spain, the fellowship was like ready. It was at hand, as Professor Eulogio said, so it was certainly a very attractive opportunity. I took it, and I went to Spain. I spent almost 3 years there. That was a very learning experience. And besides that, there was some change in my personal life there in Spain. I met who today is my husband. So when I was leaving Spain at the end of the 3 years of my postdocs, I was interested in staying close to Spain because my husband still had his contract in Spain. And luckily, I got this opportunity at the University of Coimbra in Portugal, where I got to study hadron physics from a very different perspective. I am not going to be able to talk about that perspective in this talk because of the limited time. And what I studied there was how to treat quark and hadrons as dynamical coupled system. It really gave me a very good view of what was going on in hadron physics. My position in Coimbra was actually very long. It was supposed to be like 6 years, but I stayed there just a bit less than 2 years, again for personal reasons, because in Japan we were offered 2 positions, me and my husband, and it was good. It was not in the same city, not in the same institute, but we were able to be together in the same country, and so we both accepted these positions in Japan. I was in this Osaka University in the Research Center of Nuclear Physics, which is really it was a very good opportunity. I also learned a lot in this in my stay during my stay in Research Center for Nuclear Physics. When I was finishing my postdoc at Osaka, I remember I and my husband, we were looking for settling down. We were trying in different places, and while we were trying, still giving interviews, sending our CVs, we heard from the University of São Paulo at that time that we both would work to begin with as postdocs. And we went to Brazil. It was the first time I came to this side of the world. I had never been to the Latin America. I had never been here. So I just, in all the places I went, I always went as taking an opportunity to learn. And it always has been always wonderful. When I came to São Paulo, it was very good because then some positions opened, faculty positions, and my husband got a position at the State University of São Paulo, and I got a position at the State University of Rio de Janeiro. So I worked about 3 years as a faculty there. During these 3 years, again, we were still traveling a lot on the weekends to meet each other until, which is just 4 years, a bit more than 4 years ago, I got a faculty position at the Federal University of São Paulo, which is just 1 hour and a half by public transport from the State University of São Paulo. So it's really not badly connected, very well connected. And finally, I might say that we are here settled, and it has always all the journey has been very rewarding. In this time, I have had several short stays of 1 month to 3 months, and all these stays have been useful because you always end up learning more, and you end up having common motivations, which is always good to keep you going, and that there is a lot more application of what you could have imagined of what you're doing. So I hold these collaborations with several of these institutes here. So as I would say that all my journey has been really rewarding. Let me start with the technical part. I think most of the audience here, the students, are masters, MSc students, so I don't need to go into a lot of introduction. You already know hadrons. You know that the standard model you have been introduced to. You know that the standard model, the elementary particles, are our 6 flavors of the quarks and the leptons, and we know that the hadrons are the composite particles of these quarks. So baryons are the particles which, at least traditionally, we understand their properties in terms of 3 valence quarks, and how, on the other hand, mesons, we understand their properties in terms of quark anti-quark bound state. I will show you that this view has changed, and we have many new things coming up in hadron physics these days. Oh, why am I not able to change? Okay, here. So you must have already heard in your particle physics course And you know from this book, Griffiths, at least the book I followed those days on the Introduction to Particle Physics, that in terms of these three quarks and quark anti-quark, you can describe the wave functions and the properties of the octet decouplet baryons and the mesons, pseudoscalar and vector mesons. Okay, so that was the picture roughly 50 years ago, where luckily all these hadrons could be organized nicely as these octates and decouplets on the basis of symmetries, and we could understand their properties very nicely. What is the present day hadron physics saying? Today, the number of hadrons that we know is really huge. Okay, to give you an idea, I have taken a screenshot here from the website of the Particle Data Group. The Particle Data Group is a dedicated group of physicists from all around the world, which keep up the information on different hadrons which are being discovered or studied all around the world. Yeah, so in this, if you go to the website of Particle Data Group, you will see there is a list of mesons, a list of baryons, and they have been classified in terms of their flavors. So I would say this is something very much like in the olden days, how would be the periodic table where the different elements are organized in terms of their atomic number and mass. Here we do not have one chart, one unique chart. It is impossible to put all these hadrons into one chart. There are way too many, as I will show you in a moment. We just classify them in terms of their quantum numbers. Yeah, so these mesons who are classified into the category of strange, they have strange quantum number. Here they have charm quantum number. Here there would be like the CC bars kind of mesons and similar, all those which will fit in this category. They're radial excitation, angular momentum excitation, and those that we really cannot even understand as CC bar, but they must have a CC bar content, okay, as I will show you. So I just, if I click here just in the light unflavored case, just one of them, you can see how many mesons are known today. Okay, we do not really know all of them. We definitely know the spin and isospin for most of them. So here what you see, these numbers outside the brackets are the isospin and G parity, and inside the bracket what you see is the total spin, so J, P, C, the parity and the charge conjugation parity. So we know these quantum numbers, we know these mesons, but what we still do not know is what exactly are these mesons, if they are to be understood as quark anti-quark bound state, or they have some other structures. Yeah. Already 50 years ago, when Gell-Mann and Zweig came up with the quark model, the question arises is that why would we have only two categories of hadrons where there are either three quarks or quark and anti-quark? Why do not we see other kinds of hadrons, which would be like tetraquarks or pentaquarks or blue balls, which are all allowed within the theory of the strong interaction? Nothing prohibits them from existing. But at that time, not such hadrons were not really known, or not clearly known, I would say. Several experimental searches were made at that time. Most of them brought inconclusive results. Yeah? However, more modern experimental facilities in the last 2 decades, actually less than the 2 decades, it's about 15 years ago, several new experimental facilities and modern data analyzing techniques have brought information on hadrons, which we call them as exotics today. So they are called exotics because they do not fit in the traditional picture of the quark model of Gell-Mann and Zweig. So they are something different. They are not just those three valence quark baryons or quark anti-quark kind of mesons. The clearest case, I would say, was announced around 2005 which is now called as Chi-C1 3H72. So this is the mass of the particle, okay? And it was amazing that it had a width of 1 MeV. I will tell you why all these things were so amazing, and it created a whole new revolution in the field of hadron physics. The first announcement came from Bell collaboration, and I will also tell you where is this Bell collaboration geographically in a moment. Let me just tell you a little bit that around 2005, when this particle was first announced, it was just called as X. Instead of Chi-C, it was just called as X3872. And following the discovery of this X3872, several other exotic hadrons were reported to be found in experimental data, and some of them were manifestly exotic, which I will also show you. And in those days, it was not yet clear what were their quantum numbers. For example, when this X3872 was discovered, we did not even know what was it, spin, quantum, or spin, and other quantum numbers. And it took about 2-3 years later when the spin and other quantum numbers were confirmed. So during those days, and still we have some new hadrons appearing. These last 15 years, some hadrons have been discovered, and they were labeled as XYZ hadrons. In fact, if you would look up XYZ in Inspires or even Google, you will see there are some hadrons called as, they were labeled, there were lots of discussions on the XYZ hadrons. They were called XYZ in the beginning. The idea was classifying X, which seemed like those hadrons which had isospin 0. Y were those hadrons which seemed to have some kind of strange content, and Z were the hadrons which had isospin 1. So somehow there were several XYZ hadrons appearing those days. Before I go on to explaining on the properties of this X, why they were so curious, let me organize you where are these different accelerators around the world which are focusing their resources on studying hadron physics. And there are actually several accelerators around the world, due to which we have a lot of data appearing very regularly on the topic. So we have, of course, the Large Hadron Collider at CERN, which these days is also bringing a lot of information from the B-meson decays, which is very impressive for me, because B-meson decays, the decay is weak decay, and how much hadron physics Large Hadron Collider is extracting from these B decays. It's impressive because they are rare events, and the quality of data which is coming from these decays is impressive. Then we have some smaller accelerators in Germany. I will have written information on the next slide. We have in Mainz and we have in Jülich. We have a real giant, not as giant as Large Hadron Collider, but I would call it giant because it's really providing a lot of data. It's an accelerator, electron-positron accelerator in Beijing, and BESS3 collaboration is really working hard, and a lot of information is coming from BESS these days. We have several accelerators around Japan. I will also have written information on the next slide. And in US, for example, we have the JLab, which has also been upgraded, and we should be getting new information from these accelerators too. And I will show you that there are some new which are coming up. So here, just you have the written information. In the Large Hadron Collider, we have the B decays. We have also information coming from the proton-proton collisions. In China, in Beijing, we have the electron-positron collider. In Japan, we have also electron-positron collider at Keck in Tsukuba. Slightly different location, we have J-Park in Tokai. If you go more south, we also have LEPS at Sayotown. This was closer to where I worked in Japan, in Osaka. It's closer, slightly more south. And this was at least I had some interaction with the labs collaboration, which was very useful. Where I worked in Japan, it was this research center for nuclear physics. At that time, there were 5 floors. I think they have updated the facility now. I have visited every year or every other year a research center for nuclear physics. I think they have now 1 more floor. But anyways, so we were like, the theory group was on one of the floors, at that time the 5th floor, and the experimental group was on the other floors. So it was a very good experience, because to discuss with experimentalists, you just have to go like 1 floor down or 2 floors down, or they could come up. And these discussions were very nice, because you get to see from both sides what is going on the experimental side, or what can be measured, or which information we will provide from the theoretical models, which can be useful for the experimentalist. So that was very, very useful experience. I already mentioned that in ULIS we have an accelerator, in Mainz also, in US we have JLab, and this is a new big facility coming up, Panda at Fair in Germany, so which will have anti-proton beams. And this should be working in near future. So we are going to have more data coming in hadron physics. We definitely are going to need young hadron physicists in future. And the last international collaboration before the pandemic, I attended in China on hadron physics. At least I remember 2 more accelerators should be coming up, which will focus their resources on hadron physics. If I remember, one was in China and the other was in Novosibirsk in Russia. So you see that we have already several facilities, and we should have new. So hadron physics is going to be active, is active and will be active in near future. Oh, let me go back now to this first exotic hadron, which was announced in around 2005, which is now called the KC-3872. It had the width 1, and it had the strangeness and charm. Its strangeness and charm was 0. Since its mass was in the charmonium region, it was clear that it must have a hidden charm content, even if the charm was 0. But it was then amazing that why would it have such a narrow width? It's really like a delta peak. If you have a good theoretical model or in experimental data, it appears really narrow and unusual 1 MeV kind of width. And its mass is actually more than the second radial excitation of JF psi, and it was weird that it had just such a narrow width. It decays to JF psi rho. Actually, it decays also to JF psi omega, so it has some isospin breaking. And rho, for example, itself has 150 MeV of width. So then it was amazing that in spite of its decay to JF psi rho, it has a phase space to decay to JF psi rho and JF psi omega, but it continues to have a very narrow width. These properties, together with its isospin breaking, were just not explainable in the quark model picture, at least in the traditional quark model picture. And several theoretical works were done to understand what was this weird particle. Today, there is quite a good consensus, I must say. We believe it's more like a bound state of 2 hadrons, which are 2 open charm hadrons, a pseudoscalar and a vector. So these 2 interact to make a bound state. So this Chi-C1 is not anymore a QQ bar, it's more like a molecule of 2 hadrons. Like you would use atomic physics to use the analogy to say it's more like a molecule. Okay. And although this Chi-C was discovered in 2005, we still are working in hadron physics to understand this exotic and the other exotic hadrons. As I'm showing you here, this is quite recent. In September 2020, we had some information coming on the B decays to this Chi-1 3872. And what was interesting, which was announced in this Courier or in the relevant article, is that we know that the B decays of second radial excitation, whose mass is slightly smaller than Chi 3872, its decays to psi 2s phi, psi 2s kaon, all the ratios between these decay rates is nearly 1. Okay. However, when the decay rates of these B to Chi 3872, phi, and to kaon, the ratio among these decay rates is far from 1. So this is again like reaffirming that this is something very different from the psi 2s. It's not QQ bar, it's something different. And nowadays, if we have to really confirm that it is a D and D star molecule, the challenge is now if in the theoretical models we can describe these decays in that picture. Yeah, so you see that the study is still going on this Chi-C, although it was discovered almost 15 years ago. After this Chi-C, then came some other exotics, which were manifestly exotic, which were called the ZC. They're still called Z particles. And what is manifestly exotic about them, their mass lies in the charmonium region, but they have isospin 1. So if they have isospin 1, they have the neutral ZC, and they have electrically charged ZC. So there is a charge here, but you cannot explain with the CC bar quark content. No way, right? Because CC bar will give you charge 0. So these were the hadrons. When they were discovered, it became completely clear that we had exotic hadrons, and we have exotic hadrons at hand. Just to give you an idea of how important is this topic of exotic hadrons and how many facilities and theoretical groups around the world are working on this, I'm showing you here that the first paper of Bell collaboration, which reported the existence of this hadron, has today more than 2,000 citations. So there are more than 2,000 experimental and theoretical work which have been done, which are related to this Chi-C 3872. You may ask now if it is really this is the first time we have come across the exotic hadrons. In the beginning of my talk, I said that we did not have very clear if some exotic hadrons existed. So the new ones which have been discovered more recently are very clear cases showing us that QCD has more to say than what we had heard from Gell-Mann and Zweig on the quark model. There is a lot more on hadron physics. But I must tell you that this is not the first time. Actually, if we go back in time, 40 years ago, 50 years ago, when the first excited state of the nucleon was experimentally discovered, and that of the lambda, let me remind you, lambda has a UDS quark content in the quark model, and the nucleon have UUD or UDD, yes? So these are light quarks. You know that the strange quark is heavier than the light quark. I'm talking about the constituent quark mass here. So lambda should be heavier than the nucleon. Indeed, the ground state of lambda is heavier than the nucleon. So it's about, the mass of lambda is around 1,116 MeV, and of the nucleon is like 940 MeV. So it's like 175 MeV heavier. However, when we go to the first excited state, the picture gets inverted. Yes, the first excited state of lambda is lighter than the first excited state, the one which we expect from the quark model, which must have spin half minus. This guy is heavier than this one. Now, this already brought a lot of attention historically, and in 1959, Dalitz had already suggested that this lambda was definitely something different than 3-quark hadron, the first excited state of lambda. And Dallas suggested long time ago that it is more like a bound state of anti-quark nucleon. And at that time, there was just these suggestions. I must say that more work and more data and more theoretical work analysis has been done on studying this lambda 1405 in the year around 2000, when this suggestion of Dalitz has been confirmed. And today there is even consensus from lattice. I will tell you in a moment why why I give so much weight when we have consensus also from lattice. I will tell you which are the different options, theories we use these days to study the hadron physics. In the next few slides, I will be talking about it. But what I want to say is that there is a consensus now on that this first excited state of the lambda itself was not fitting in the picture of the three quark or three valence quark model, and its properties are now understood more in terms of the K-bar bound state. It's not really a bound state because it has a width, but let me just put it in a simple way. It's something like a K-bar bound state. These kind of hadrons, there are several of them now known. They are called either molecular or dynamically generated hadrons. Okay, they are dynamically generated because they are generated from the dynamics of the hadrons themselves. Okay, we don't really need to go to the quark degrees of freedom. And we use the analogy in the atomic physics, where, for example, you have a hydrogen and two hydrogen and oxygen. To understand the molecule of water, you do not really need to go to QED to understand those properties. And it's more like a weak interaction between the atoms, which binds them to keep these molecules. So we use this kind of analogy to call these kind of hadrons as molecular or dynamically generated states. You might ask exactly what are these states, okay? I will give you a bit more detail on how these states are studied. Actually, I study a lot of them, but just to give you a very quick idea, it's like you build an effective field theory where you have no quark degrees of freedom. You have only hadrons as your degrees of freedom, and you let those hadrons interact. So you solve infinite order scattering equations. And then what you suddenly see is that you have a deuteron-like bound states. It's deuteron-like, as I said, it has a width, it's not exactly a bound state, but it is not in your dynamics. You just have dynamics of two hadrons and it appears as a bound state. How does it appear? You will be able to understand this more in a few more slides later, but let me just show you here quickly that this is this squared amplitude which you see in the complex plane, and what you see is that suddenly this kind of peaks appear, infinities appear, which which have some width, so you can read its real part of the energy, and the imaginary part of the energy is interpreted as the width of these hadrons. This is how you find these kind of molecular hadrons. Yeah, you can ask, can we study these kind of hadrons? Any of these, not necessarily molecular, or exotics, or even others, can be directly studied using the QCD Lagrangian, and I will tell you that that is not possible. And that is because QCD has a limitation. It's not limitation, it is the nature of the strong interaction, which makes that the QCD becomes non-perturbative precisely at the energy of region of interest for hadron on nuclear physics. So, for example, even nucleon-nucleon interaction, we cannot understand directly using the QCD Lagrangian. Let me tell you what is the meaning of that QCD becomes non-perturbative. So just to understand, you see in more detail QED in your courses, and you know that if you're studying electron positron scattering, you can have such diagrams, or you can have these higher order diagrams. And what you know is that if you go on adding higher and higher order diagrams, you get corrections, right? So you would be able to get your amplitude or other information of the observables, you get with more and more precision, because these higher order diagrams, they provide corrections. They provide corrections because this coupling, this vortex, the electromagnetic coupling, is less than 1. So when you when you start adding the higher and higher order diagrams, at some point you have a convergence in the series, so you don't need to go on adding more and more diagrams. However, in strong coupling in the QCD, this coupling, the corresponding coupling for, so it will be here quarks, this coupling is bigger than 1. And in the energy region we want to study the hadrons, it's of the order of 10. So it's so big that every diagram you add, you do not get corrections. You actually get every time a different number. So there is no convergence. You cannot sum up higher order diagrams perturbatively. So the QCD becomes non-perturbative, and it's impossible to handle it if you want to study these hadrons. So then the question would be, what are the alternatives we have? We have several alternatives. And here I have already mentioned to you lattice QCD, which is the closest to solving, studying QCD. So lattice QCD is exactly taking the QCD Lagrangian, what you study in finite volume. Yeah. So when you study in finite volume, you do not have this problem. It is perturbative in the finite volume, but you have other challenges. And the other challenges will be you study your system, your hadron, in finite volume, and now somehow you have to project your results on the infinite volume, because the real world is infinite volume. And these kind of challenges have been faced, and there are solutions, excellent solutions, which have been brought up by the lattice theorists around the world. And actually there is a lot of progress. We have very good results coming from lattice QCD. However, we are still far from studying scattering and getting hadron, studying the properties of the hadrons, these exotic hadrons, and calculating observables related to them. And not saying that the information, the exotics are also being studied on lattice QCD, but still it requires a lot of computation, and there are some more challenges which are being faced. The other alternative, which is also popular around the world, is called holographic QCD, where one uses a relation between the anti-de Sitter spaces in the string theories to the conformal field theories. I am definitely not any expert on this topic. Also, I do not work on lattice QCD. There are other options, which are the QCD sum rules. I will not be talking about the QCD sum rules in this talk because of the limitation of the time, but let me quickly tell you what one does in QCD sum rules is that you want to study a hadron, and what you do is you write a correlation operator. Okay, and you make a Wilson an expansion of it. So then for each quark line for the hadron you want to study, you have all kind of non-perturbative corrections. And then that is one way of studying your hadron, your correlation operator. And what you try to use is the fact that there must be something which can be somehow used at lower energies to describe the same, let's say 4 quark as a hadron. So there are two sides of studying these QCD sum rules. One is called the QCD side, where you take the quark lines and you start adding all kind of non-perturbative corrections to each of the quark lines. It's quite involved calculations. And then one is the phenomenological side of description of the same hadron. And this phenomenological side, you give some kind of, you use some kind of an ansatz to describe its properties. And what you try to do is that you say that at some energy, these two pictures must coincide. Okay, and then using this, you can study the properties of the hadrons. The other are the effective field theories, which are inspired by QCD, and this is what I will give you an example on. Quick examples. And other options, you still have phenomenological models where you can use the experimental data, and then you can study your system where you have some data, and inspired on the data you can build some phenomenological models. So let me quickly go over to giving you here an example. So this, if you want to study, for example, pseudoscalar meson baryon interactions, one can use the Carl Lagrangian, which is very well studied from the 1990s. Sorry, so it's an effective field theory inspired by the chiral symmetry. We know that the chiral symmetry plays an important role, and its spontaneous and dynamical breaking is an important part to understand the pseudoscalar mesons as the Goldstone bosons. So let me show you here. This is the Lagrangian. Just to quickly have an idea, so these are the fields here. This is baryon, anti-baryon field. This is exactly like what you do in your toy theory in Feynman. You write a U bar and a U for incoming, outgoing baryons. And this gamma is related to these kind of fields, where P is a pseudoscalar meson. I'm telling you this because you should see here that everything written here is in terms of the fields of the mesons and baryons. There are no quark degrees of freedom. So your degrees of freedom are mesons and baryons. So this is something which is well known from 1990s. And this is where we extended the studies of the pseudoscalar mesons to vector mesons. So here will be my contribution, where we studied in a very bit detail how we could extend the pseudoscalar mesons now to vector mesons. And here we have used a symmetry where vector mesons are used as the gauge bosons. So it's called the hidden local symmetry. Based on those symmetries, we studied several interactions, and these are, you have to sum up all of them. Yeah, again, please see that in this Lagrangian, you have the vector meson fields, you have the baryon fields. And this is a relation which is based on the partial conservation of axial current, which is historically again related to the chiral symmetry and its spontaneous and dynamical breaking. And these F and D couplings are related to the axial coupling of the nucleon, again related to the same thing. So everything here is known, and you put in your degrees of freedom, which are the hadrons, and then you also have a Lagrangian which takes you from one pseudoscalar meson baryon to vector meson baryon, again in terms of the hadron degrees of freedom. The next step would be that you start writing all kinds of meson baryons which have, for example, a given quantum number, because all of them couple to each other. So here I'm giving you all the meson baryon system you must include if you wish to study strangeness -1 systems. Once you have all these interactions from the Lagrangians I showed you in the previous slide, then you have to put in here, this is your input, and then you solve this infinite order equation. Scattering equation is called the Bethe-Salpeter equation. And this is a matrix equation because you are going to study them as coupled channel. It's not just a simple equation. Here, each of this term is a matrix. So when you solve this equation, you obtain your amplitude. And now you can see, you can take your amplitude, you go to the complex plane, and then you see appearance of this kind of dynamically generated on molecular hadron. This is how you study them. Yeah. We studied the strangeness, precisely the strangeness -1 meson baryon system quite recently actually, and we made sure that we could explain several relevant data on the related to the strangeness -1 meson baryon systems. And what we found is that we could study very well the properties of the lambda 1405, and we see that its isospin 1 analog also appears in the complex plane, so it's also a molecular resonance. But this one is not very well known. There is a lot of discussion on this hadron. I remember giving this talk in Japan, and an experimentalist from Leb's group suggested that it would be useful to predict how these hadrons can be studied in some reactions, such that the experimentalists could feel motivated and plan some experiment to really study production of these hadrons. So then we started discussing, me and my collaborators, and then we thought that if we want to show, for example, the photo production of sigma, if it is feasible, what kind of cross-section one gets, then we need to study these kind of diagrams, these kind of Feynman diagrams. And then we realized that we actually need also some kind of exchange of the nucleon and their resonances. We saw that some of the nucleon resonance lie very close to the threshold of the threshold of this process. And here, by the way, here Y star is either this lambda or this sigma. And that brought us to another motivation, where we had to study how these N stars are coupled to GYAN and these HYPERONs, low-lying HYPERONs. This was a very involved study. As you can see, it was published very recently in the beginning of this year. Here we studied, we took all kind of possibilities, how we could relate this N star to a final state of GYAN HYPERON, just to give you a flavor of how the amplitude looks like, and then you use your Feynman rules to write this numerator, which looks like this. Then you can separate the 0 component and the 3 components, and you can then write some kind of a summation, a series here. And then in this series, you have these coefficients which look like this. And then you can do the Q0 integration analytically. And what I want to show you is that you cannot proceed further, because here you get some kind of terms which you can write in terms of numerator and denominator as a summation of that. And the numerators look like this. So you cannot really do any more analytical calculation. You must do some kind of numerical calculations. And when you do numerical calculations, you find such kind of results. So these were our results. This is the information known from the experimental data. And what you can see here is this particular nucleon resonance has this kind of branching ratios, and we brought attention of the experimentalists to the fact that the decay of the N star 2 HYPERON resonances has comparable branching fractions, and we motivate the experimentalists to look for the properties of nucleon resonance in these kind of processes. So it was very, very interesting finding for us. And once we had this information, we studied the photo production, and we are giving here, So we are predicting how the cross-section would look like. The cross-sections are very much measurable, and we are now hoping that this will motivate future experimental searches of these hadrons. Let me quickly give you also how one can study more than 2 hadron interactions. So if we have 3 hadrons if we want to study 3 hadrons system, then you cannot have just 2 hadron interaction. You have something which is called a Faddeev equation, which is sum of the 3 infinite series. So you just don't have one, you have sum of 3 infinite series, which are actually coupled series. It's difficult to see here. I'm just showing you here diagrammatically one of the series. So this would be a series where you have, for example, interaction between particle 2 and 3, and after particle 2 and 3 interact, particle 1 and 2 interact, and then you take all kind of permutations into account. Exactly like this, you would have 2 more series. You would solve all of them in coupled channel calculation. Now this kind of calculation is really involved. The code we wrote to solve this kind of solution of this kind of equations it sometimes takes weeks to run and to get the amplitude. But it is also very interesting, because we have found that not only 2 hadron but also 3 hadron systems can form bound state or molecular resonances. Here we are predicting a K-star resonance, which would be in the charmonium region, precisely where the Bell, BESS, and other experimental facilities are focusing right now, so they can easily find this K-star resonance. We have also studied if we can get a signal of this K-star in B decays, because the Large Hadron Collider focuses on getting data from the B decay. And we actually see that the B decay to J psi pi pi k on this final state, the data is already available. Only thing is that the invariant mass spectrum of J psi pi k has not yet been reconstructed. So far, only pi J psi pi invariant mass spectrum was reconstructed, actually where the chi C 3872, the first exotic I said in this talk, was found. So what we have done in this work, we show that in the B decay, in the other invariant mass spectrum, this hadron K star hadron will be clearly seen, and there will be some background. There is yet another 3-hadron example I want to show you, because it is also something which we studied again recently. The first time we studied it was in 2008, where we saw that phi k bar, they form a kind of a bound state, and this is how the bound state appears in our amplitude. Okay, and very recently with the updated data, we show how we can describe the data very nicely. And in this latest data in 2020, just last year, Best published the decay of this phi 2170. In those days when we studied it first, it was called as Y 2170. Its decays to different kaonic resonances have been published in 2020. And we studied these branching ratios, taking into account several diagrams, quite involved sometimes. And we show here how experimental results and our results are very much compatible. And I must call your attention to the fact that it is not at all trivial. It's not at all easy, because the same processes have been studying by treating this phi as a QQ bar, as a tetraquark, or as a hybrid, within many different pictures. And in none of these pictures, it was possible to explain this data. So it is a remarkable finding. Again, this was published in the very beginning of this year. I would like to also show you that not only mesons, there are baryons, exotic baryons, which have been announced. This is an announcement from CERN, also in 2019. It is one of the systems which I am studying right now. I do not have the results yet. One could ask a question. Okay, besides all that wonderful agreement between the experiment and theory, what are we getting from this information? One of the things which we are doing by studying all these hadron physics, all these interactions, is uncovering the working of strong interactions at low energies. You have already heard from me in this talk that the QCD is non-perturbative in the hadron nuclear physics region, so we do not even understand the nuclear matter directly from the QCD. And all this, how exactly strong interactions work at low energies, is a hidden information. And the only way we can understand this part is by studying the properties of the hadrons and their interactions. Besides the existence of hadron resonances, be it exotic or non-exotic, they are important. This kind of information is important because it is very useful when other kind of research, which is like the heavy ion collision, when they have cross-sections, very often they have cross-section or yields, which they are not able to understand when they are taking into account the information from, let's say, non-exotic or hadron-hadron interaction. And then they need more detailed hadron-hadron interactions, or sometimes, for example, if they have yields of D mesons or anti-D star mesons in heavy ion collision, it could be that the yield is much less as expected, and that is because the several D and anti-D star which have been produced in the heavy ion collisions, they have recombined and formed this chi C, which has only 1 MeV of width, so it's very stable particles. And so for some time, it's going to be like why the D and D star mesons suddenly got depleted from from our expected yield. And then the information on the hadron interactions and their properties is very useful in understanding this kind of Hebbian collisions. One also needs such information to understand, for example, the data from the cosmic showers. So hadron information is really useful from many different perspectives. Besides already knowing that we have the strong interaction is not just limited to finding of hadrons, which were in the traditional quark picture. There are exotics, and these exotics, they matter in different kind of processes where the data appear and the data suddenly look weird, and we need these exotics to explain why those data appear to be weird. Besides that, there are also applications to real life. I mean, hadron physics. Very often when we study fundamental physics, we are not really looking for applications. The applications actually just sometimes come by. Yeah, they happen to appear, and it's just because we have already had some information because we were studying some fundamental physics. So for example, you might have heard of the PET scan, which is used in hospitals. This PET is positron emission tomography. So thanks to the knowledge we have on the antiprotons, anti-electrons, antiparticles in general, we are able to use the antiparticles in medical research in the daily life. Actually, just quickly, I'll tell you how this PET scan is done. Normally, a patient is given some kind of a medication which is radioactive. It will emit the beta, so an electron, and then when the patient goes back to the hospital, an electron beam is directed to the patient, and these positrons and electrons emitted by the radioactive material interact with the positron, and taking into account how these interactions occur, these detailed interactions, we can reconstruct the image of the different parts of our biological parts. Yeah, so you can see how sometimes the fundamental particle physics can be useful. Besides that, at CERN, there is a dedicated research on how antiprotons can be used for cancer treatment. These days, proton and even other hadrons, how they can be used in diagnosis and in treatment. In medical research, as in medicine, there is a lot of research going on. Not my field of research, but there is this application. And I am closing my time, which I must have used. So I'd like to summarize. I hope in this quick talk I have shown you that hadron physics is very open and active field of research. There are many facilities, many theory groups around the world dedicating their time and resources. And there are new facilities which are going to come up. So we're going to have more hadron physics news surely in the near future. And the main challenge, I hope you have got the information that the main challenge is the property of the QCD itself, which is non-perturbative. The strong interaction at low energies makes that the QCD is non-perturbative, so we cannot use it directly. So there is also a challenge of using different kind of alternatives and how we use these different kind of alternatives. So sometimes, for example, I study a system with the effective field theories, and then I use the QCD some rules also. So if I'm using many different formalism and I end up with different same results, then it makes me feel more confident. So this is also another kind of procedure one does. So what one has to do is a very careful research when one has to be studying these hadrons in the present day. And I hope I have convinced you that hadron physics has lots of charm and lots of strange information coming up, and it is quite exciting. And I thank you for your attention.